Okay, good morning everyone. So, a new week, new subjects for the course, and also this week, as you know, you will start with a practical work this afternoon. I hope you already checked the first assignment, what it is, so you have questions for us this afternoon. So today, let's see, we'll talk about key distribution and user authentication, subjects that are linked together. So we'll start with key distribution, and then we'll look at two different standards, the Kerberos standard and the X509 standard. And then we'll talk around a number of different standards, both for public key infrastructure and for federated identity management. But the two main standards that we look at are these two, Kerberos and X509. Anyone already know what Kerberos is used for?
It's security for system administration. I don't know that. Like if you have like this database for a company,
Yeah.
and you gotta administrate like computers for many people, and Kerberos is it's like widely spread, like also with this Windows thing.
Yeah, exactly as you say.
I just don't know how to explain.
Yeah, but it's as I say, we are inside a company, we have a number of different services and different computers, and you have a number of users who would like to access all of these different services. Then Kerberos is a system that is used to authenticate and make sure that you can access what you should be able to access. And also, exactly as I said, it's used inside Windows today as a way to authenticate users in a distributed system. X509, what is that in general? Yep. Yeah, a system to how to create and manage certificates. Again, let's see, I have to change again here for my screens. Let's see if that one works better. Yep, that's better actually. So, key management and distribution. We talked about that for when we talked about encryption algorithms. Because it's the keys for encryption algorithm typically that we need to manage here. We have now an encryption algorithm to make things secure, and we said that we need to distribute the keys somehow. We already seen that there is a difference between symmetric and asymmetric encryption in terms of how difficult it is to manage and distribute these keys. For symmetric, both parties need to share this common secret that we have and somehow handle that distribution. For public encryption, it's easy to distribute the keys, but we still have this option that we need to have some trust in the keys. And if we look at many different systems that we use, actually uses both symmetric and asymmetric encryption. So we need to be able to manage both types. With symmetric, it's the actual distribution that is the main problem then. And it's not only that we need to be able to distribute keys, but we also need to be able to distribute keys quite often, because we are often using two different levels of keys. We have one that is called a permanent key, we'll come back to that. that we share for a long time. But when we actually encrypt things, we use session keys or temporary keys. And we can change these quite often. That can be many times a day, for instance, that we change these keys. And each time we change a key, we again have to distribute them somehow. So it's not only that we need to find a simple way to distribute keys or a way to do it a few times. There are some concerns, main concerns about the key here: confidentiality and timeliness. Confidentiality means that, of course, what we talked about, confidentiality, to keep information secret. And I mean, that is why we encrypt from the beginning. We encrypt something to keep it confidential. But the key that we use to get that also need to be confidential then, or we have to maintain confidentiality for it. But we also have this aspect of timeliness. When can we use a key? For how long time can we use a key? Does a key have a lifetime? And what happens after that lifetime? Often we would like to limit for how long a key is valid to handle, for instance, replay attacks. Because if someone is actually able to capture our key, we would like to limit for how long time it can be used. And if they capture a packet that is encrypted with an old key, we would like to make sure that they just couldn't resend it and it will work again. So different types of replay attacks or attacks on the use of a key. Yeah?
What's a replay attack?
Well, a replay attack is that we resend a message that was used as a legitimate packet. And if we take it to the extreme, if we have a new key for each packet, a replay attack wouldn't work. In most cases, we don't do that. We encrypt a number of packets with the same, but as soon as we change keys, all old packets will be useless for a replay attack. So let's concentrate first on the symmetric keys and see how we can handle the distribution of those keys. Here we have 4 different models for it. So the first one, that the different parties A and B here meet physically and exchange keys or deliver a key. That is of course secure, but it's not working in normal situation. I mean, we couldn't meet everyone that we would like to change keys with. And especially since we now said that we would like to change keys quite often, we couldn't meet regularly to do that. So 1 doesn't work. 2, a third party could select the key and physically deliver to A and B. So now we involve another one, another party here. Let's see. So we have A, we have B, and now we have a third party here. And both A and B meet this third party to exchange the keys that then later on will be used to communicate with A and B. Is this a simplification? Yeah.
Who generates the key?
Typically it would be the third party who's doing that. But it could also be that the third party is only a delivery mechanism, so it's either A or B who creates it. That could be different situations. How does this improve a situation compared to 1? Well, you have to meet the third party.
Or the third party goes to you.
Yeah, depends, of course. But if you compare with in one we only have one physical trip here to change the keys. Now we have two. So it seems that this is actually a worse situation. But there is an improvement here. What is this improvement?
If you trust the third party, then it works better than trusting me.
Exactly. This third party can be someone we trust. A and B might not know each other. They meet, but we don't really know who we meet. But if we trust this third party who knows who A and B, the third party can vouch for them and make sure, yes, you have exchanged keys with the correct party. And also, in a situation where we have hundreds or thousands of users, each of them only needs to meet this third party, but don't have to meet everyone else. So we have limited the number of physical exchanges, which would grow exponentially otherwise. Yeah.
We also have the problem that we have to trust the third party totally, because in some cases they even have the control over our keys.
Yep.
Total control. And also third party is a weak point. Like if you want to attack this kind of the conversation between A and B, we just have to attack the third party now, and we basically shut down the whole communication for everyone.
Exactly. The third party here is now a crucial player. We really need to have a trust in the third party. Otherwise, this wouldn't work. And it is a point of failure for the entire system, as you point out. Okay, but it's still quite tricky to handle then. It's not very practical. So let's look at number 3 then. A and B have previously used a key. One party can transmit the new key to the other, encrypting using the old key. How will this help the situation?
Why are we changing the old key?
Sorry?
Why do we change the key? Because if you have the old key, why are you changing to a new key?
Yeah, why would you change the new key? Anyone? Why do you want to change keys? Well, we talked about this before here. The replay attacks. We want to exchange keys regularly. But how will this help? Well, the help is, of course, that we only need to meet physically once. If we didn't have this possibility to encrypt and exchange keys, we would have to meet regularly. But now we only have to meet once. But we still have this problem that we actually need to meet. And then we have number 4, where we again add the third party here. A and B each have an encrypted connection to a third party C. C could deliver a key on one of the encrypted links to A and B, and then it would look like this then. Up here we have this third party. We call this a key distribution center. We have what's called front-end processor that automatically handles and delivers keys if needed. And then we have A and B here. So A starts with creating a message that should go to B. The front-end processor captures this and sees, okay, now we need a key because we don't have a key right now to be able to send this packet. So using an encrypted channel, we send a request to the key distribution center to generate a key for us. And the key distribution center delivers that both to A and to B. And then we encrypt the packet using that key, send it over here, and it can be decrypted. And all this can be handled automatically. The only thing that we need to do is set up these secure channels with the key distribution center, and we only have to do that once for each user that is using that key distribution center. Can you see any weaknesses in this scenario? Yep.
The key we are using right now is compromised. The attacker could for us.
You mean the key that we have exchanged between the key distribution center and one user?
Like
Or-
if I was an attacker, I got hold of your key, and I would just go to the third party and change this key to another one, and basically you could never get hold of it again.
Well, if it's changed, of course, I would recognize that immediately when I try to communicate with someone else, because then it would fail. I wouldn't get a new key. So I would get a signal something's wrong, and then I can set up a new key with the key distribution center. So if the key is compromised, yeah, I can lose some packets, but I should be able to recognize it quite soon that something is wrong here. Yeah.
Key distribution center could theoretically always listen to the session.
That is an possible problem here. If they create all the keys here, they can listen into any conversation that's going on down here, because they have distributed the keys. There are ways to handle that, so they can create the session keys and deliver them without actually knowing what the key is. So it's possible to handle that. Yeah.
My question might sound stupid, but how can they listen to the keys if the communication is like? Does all communication always go to the key distribution center?
No.
No.
But if they can capture the traffic, I mean, this is traffic on the internet, they could possibly capture it somewhere. So this model requires us to really have trust in this key distribution center. Regardless of how it's implemented, we need to have that trust. But it's also that trust that makes it possible for us to start communicating with anyone else that also have this trust in the key distribution center without knowing it. So it's a double-edged sword here. Another problem with this model is that it would only work in a full scale if everyone on the internet was using the same key distribution center, because we need to have trust in it. And that solution doesn't exist. There isn't a key distribution center for the entire internet. So for the entire internet, this is not a working solution. But it can be a working solution in a limited area. And that's exactly what Kerberos will show us. Just go back to this slide with the keys as well. As I said, we talked about a permanent key. The permanent key then is this key that we have set up between each user and the key distribution center. And the only thing we encrypt here are keys. And the key is very small, so we can encrypt that for a very long time before we start creating a lot of information. But each time we communicate here, we ask for a session key, and the session key is what is used to encrypt actual data that is going between the nodes here. So, Kerberos, the many-headed dog that guards the entrance to Hades and won't let anyone in who shouldn't let in. So it's a guardian of something important. It's a system developed at MIT, and the ideas behind it was to handle authentication within an organization, and to do that based only on symmetric encryption. Nothing to do with public encryption at all. And there are different requirements here. There are a number of different workstations. There are a number of different servers. And a user at the workstation should be able to log into different servers. There are different versions of it. Currently, number 4 and 5 are still in use. And as we mentioned before, internally Windows is using Kerberos for handling authentication in distributed networks. So, we have a user somewhere at a workstation that would like to use a service. Could be an email server, print server, file server, whatever. What we need to do now is to authenticate and prove, yes, I am that user, I can use that service, and also check that we have the access right, that we have the correct type of use for it. And that's what Kerberos can do. There are some typical threats that they looked at when they created Kerberos. One threat could be that the user pretend to be another user. How can we do that? Well, if we claim to be another user by capturing the username, then that of course possible. How do we typically handle that? Well, we typically handle that by having some type of authentication, typically password. In Kerberos, they also link a user to a certain computer. So you couldn't pretend to be a user from the wrong computer, then it wouldn't work. So that's where this attack coming from. A user alters the network address of a workstation. Since we are linked to a workstation, we can spoof our address and say that we are on another address, even if we're not. That is also a typical attack that Kerberos would have to try to handle. And then, of course, eavesdropping is a threat. People listening know what's going on in the network, check the authentication process, maybe can read that information and reuse it, or capture parts of the packets in a replay attack. So these are also things that we need to think about. There are opponents who could eavesdrop and capture the traffic. Some terminology that Kerberos is using. C is a client. AS is an authentication server, so that's where we authenticate, prove who we are. V is a server for some useful service like web, also mail or print or whatever. ID C is then the identifier of the user on that client C. IDV is the identifier for the server that we want to use. PC is the password for user on C. And AD is the network address that we are currently on. Then we have a key, a secret key, and that is actually an encryption key. So for the secret value we use an encryption key. That is also our way to authenticate, by knowing that secret value. And there are actually several, but we start with this one. KV is an encryption key shared by the authentication server and V. So this means that before now we have set up a situation where all the different servers already have an connection with authentication server. They have changed keys manually, probably. So we have a way to securely communicate between the different servers and the authentication server. We have timestamps and concatenation, where we just, when we build messages, we put together a number of different items here. So what do we need to do? Well, we need to have some exchange here. So this is the first attempt to build Kerberos then. We start with number one here. From the client, we send a message to the authentication server. And what we're saying is that we are this user. This is our password. And this is a server that we would like to access. With this information, the authentication server can now decide first, are we who we claim we are? Because they have our identity and our password. They can check that we have actually access to that server, that we have authorization to access that server. And if all of the things tick, what the authentication server is doing is sending back a message to the client. And that message is what we call a ticket. And down here we see what that ticket contains. The ticket contains information about who we are, our password, and what server we have the right to access. And all of this is, as you see, encrypted with a symmetric encryption method and using the key that is shared between the access server and the client and the actual server. Who can read the information in this ticket?
The server and the authentication server.
Yeah,
So V and AS.
V and AS can read that information. Who gets the information?
First C, then V.
We send it to C, the client. So this ticket that the client gets, the client couldn't see what it contains. It's encrypted. Of course, there is information about the ticket, so we know what it is, but the content of it is actually encrypted, so we couldn't do anything about it. Yep.
Is there a timestamp in the ticket?
Nope.
So basically, you could always reuse that ticket.
Yeah, right now we don't have any timestamps, so a replay attack would work, yes.
The ticket is actually encrypted, but the communication from the client to the authentication server isn't. Is that where you would be able to get a password if
Yeah,
someone...
you pointed out an obvious problem here, that the ticket is encrypted. So in the next exchange here, when the client contacts the server and saying that we are whoever we are, and this is a ticket saying that we have a right to access you. The server can now decrypt this ticket because it has this key, and it can check that, yes, we are who we are, and the authentication server have checked that, and so everything is okay, we can access it. And then we will get our service. But exactly as you point out, in the previous exchange here, we don't have an encryption. So that is an apparent problem. Anyone who listens into the communication can read this and read who we are and what our password is. And even that means we don't have to even do a normal replay attack. We can just use that information, password, from anywhere to authenticate again against some other server. You pointed out another problem, that we don't have any timestamps, which means that this ticket is valid forever. So that's another problem. A key can be compromised later on, or we may want to limit for how long time a service can be used, but that's not possible here, because once a ticket has been granted, it is forever valid. So there are some problems. One way to handle that problem would actually be to require an authentication each request, so there's only one time. But it's very hard. In our exchange, we haven't seen a way to mark it as just one time. And even if we had that, it wouldn't be very nice, because that means we will have authenticate each time we would like to use a server. We don't want to do that. A third problem is the servers. That if we want to access a new server, we would again have to authenticate, even if we just have done that. We are still the same person, but we have to authenticate to get a ticket for another server. So we have to improve the protocol a little bit. So this is an improved version of Kerberos then. As you see, we now split up the communication in 3 different phases. The first phase we use just once per what we called log-on session. And a log-on session could typically be once per day. So we have to authenticate to the system once per day. If we have very high security requirements, we can say that it's only valid for 2 hours, for instance. And then you have to re-authenticate each 2 hours. It's up to us to decide. But that is one session then. But once we have done that, we don't have to authenticate each time we use a server or each time we use a new server even. We just have to do it once. So in the first part here, the client communicates again with the authentication server. The first exchange says that I am IDC here, and I would like to access not a special server, but something called a ticket granting server, TGS. So what we do now is we split up the process of authenticating in 2 parts. First, we authenticate who we are, that is to the authentication server. And then we have to go to the ticket granting server to get authorization for a certain server. So we split up the process up in 2 steps. So in the first step, we just say that we would like to access the ticket granting server. And if the authentication server says, yes, you are a valid user here, it will send back a ticket to the client. And let's see here, what do we have? What we send back is an encrypted message. Inside that encrypted message, we have a key. And that is a shared key between let's see here now. No, sorry, it's not. What we say here is that we encrypt it with this key, which is the client key. So we have a permanent key between the access server and the client. So we have a ticket here that is encrypted, so this is a parameter for the encryption algorithm. So it's a ticket. And if we look at the ticket, we have more things now. We have information about the user. We have information about from what computer the user is logging in. We have information about what ticket granting server we would like to access. And now we also have a timestamp and a lifetime for this ticket. So know when it was created and for how long time it can be used. And all of that is encrypted with another key, the key that is shared between the access server and the ticket granting server. So let's just look at this first exchange first. We see that the first message is not encrypted still. Is that a problem? Yeah?
If the client's requesting to the no, wait, no. It doesn't make sense. Never mind.
Okay, anyone else? Well, what does it contain? It contains information about who we are and what we would like to access. Our password is not here anymore. That has been removed. So anyone who would listen in would only see that, yes, this is me, and I would like to access the ticket granting server. Nothing revolutionary. I mean, this is information that is pretty obvious what it is actually. So it's not a problem that that is encrypted. But how do we check the authentication? How do the client prove that we are we? Yeah?
Decryption of the return.
Sorry?
With the decryption of the returning packet.
Exactly, with a decryption of returning tag. Because the message that sends back here is encrypted. And the only one who can decrypt that is the one who knows this client key. So we send an encrypted packet back, and anyone can see it, but only the client can decrypt it. And once we have decrypted it, we have now a ticket. If we don't decrypt it, we don't have access to the ticket. Yeah.
Does that mean that the authentication server has keys for everyone? Like the key for each user?
Yes, the authentication server have these keys for all of its users. So we have exchange keys with all users, and it also have keys for the ticket granting server. But that is typically only one ticket granting server in the system actually. But yes, we need to manually distribute keys for each user. Okay, so now what we have done is we have authenticating, proving that we are the person who we are, and we have a ticket that makes it possible for us now to start trying to use services. And that is what we use down here. So for each type of service that we would like to access, the client sends a request to the ticket granting server saying that I am me, I would like to use the mail server, for instance, and this is the ticket I got from the authentication server to prove that I am a legit user and who I am. The ticket granting server now checks that I have those access rights, that I have access to that server. And if that turns out okay, the ticket granting server will send back a new ticket here to the client. That ticket, as you see, is encrypted with a key that is shared between the ticket granting server and the actual service. So that means that the ticket that we get back here from a ticket granting server, we can't decrypt. We don't know what it contains. But what we can do is we can pass it on to the server, and that is what we do down here. And the server can decrypt it because it's encrypted with a key that is shared between the ticket granting server and the actual server. Yes?
You said on the first step, it's not a problem that this ID and this is not encrypted. But you know, the attacker can know the routine of the user. Like we can, this user usually at this time access to this server or something.
Yeah.
So it's not the problem.
Yeah, that's true. The information here in the first exchange is not encrypted. So what we have is thing reconnaissance or prepare for an attack later on when we just gather information about the network. And yes, since it's not encrypted, we can learn about who are the users of the system, when are they active and so on. So that is the information that we can gather. But we couldn't use it to get into the system, but we can get information. So yes, that might be seen as a problem. Again, this new ticket have a timestamp and a lifetime, which means that if we get a ticket for the mail server, for instance, that can be valid for a week or just an hour. If we need to get a new ticket because it has run out, we don't have to do authentication again. We can just ask the ticket granting server to get a new ticket. And all that can be handled automatically. The only time the user has to be involved in when we have to type in our KC here to when exchanging information with authentication server. But the rest of this exchange can be handled automatically for us. Okay. Unfortunately, this is still not enough. There are still flaws in this exchange. The problem one is that the lifetime here means that, well, how long should the lifetime be? Well, if it's too short, we have to ask the user again for authentication. I mean, in the first exchange here, when we are contacting the authentication server. And if it's too long, then there might be opportunities for replay attacks or gather information and crack the key and use it somehow. Second problem is that the rogue server can give incorrect credentials, because what we do down here in the third step is that the client sends information to prove who he is to the server. but the server doesn't have to do anything. So a rogue server could set up a service, and then the client accidentally connects to it. He sends a ticket that the rogue server couldn't do anything about because it's encrypted, but he just throws it away and says, yes, you're now free to use my service, and starts to store files on it, and those files can now be stolen or something like that. So the client has no idea to know who the server is, which is a potential problem here. There are a few other problems, but the effect is that we have to add even more information. And now we won't go into the details as much because it is a little bit more complex, as you see. The main idea is still the same. We have a first exchange between the client and the authentication server. We have a second exchange between the client and ticket granting server. And we have a third exchange between the client and a special server. But now we also have a return here so that the client can validate the server as well. But as you see, we have to add more information in the exchanges. So we have more timestamps, and we have something called an authenticator. And the idea with these authentication is that we can actually validate each packet that it's not a replayed packet, because otherwise tickets can be reduced. But the authenticator makes it possible to validate each packet actually. So the information is quite complex. There are a lot of things. Things are encrypted pretty much the same way as the previous exchange, but we have more information. So, how does it look then? Well, it looks like this then. A typical system that is using Kerberos. Here we have a user. Here we have the Kerberos system, which is split up in two different servers, but often they are actually merged into one service on the same machine. And then we have different servers for mail or file and so on. So the client contacts the Kerberos system to authenticate, get a ticket granting ticket. We take that to the ticket granting server, and we get different tickets for each server we would like to use. And then we contact the server with these tickets, and now we can start using that service. And if we would like to use another service, we just ask the ticket granting server to get a new ticket, and then we send that to the other server. And the user is only involved once per login session than when we have to authenticate the first time here. And this is another way to look at the changed. First, we communicate in the first step here with the authentication server, in the next step with the ticket granting server, and in the third step with the actual server or service provider. Now, we can extend Kerberos a bit, because we said that in Kerberos we have a server, and all the users need to be registered in that server, and we have to exchange keys somehow for each user. So it's typically a system that is used within one company, one organization, because we need to have control over users and be able to distribute the keys. But sometimes we would like to extend the reach of that. And a Kerberos realm is a server, a number of clients, and a number of applications. But say that we start to work together with another company, and we work quite intimate together, so we need to share each other's resources and so on. Each of them have a Kerberos system, but the users in my system is not known in the other system. How can we handle it? Well, one would be to just replicate the information, so both realms have information about both users. But instead of using that, we introduce this concept of inter-realm communication. So we can say that in one realm where we have one authentication server, we can grant access to another realm. So we start here with a client exchange. The client asks for permission to use a service in another realm. And then once we have that, we contact the ticket granting server in the other realm. At this stage, these two realms are connected. So whenever a request comes from another realm, we say that, okay, they have already authenticated. We don't know who this user is, but it's checked by the other realm, so we'll go with that. And when a request comes here, we will get a ticket to actually use a service in that other realm. So we don't have to send out the information about all of our users to the realm. We only have to create this trust between the two different realms. If you look at versions here, version 5 was developed in mid-90s. Introduced a number of improvements, both in terms of functionality and in security changes. So if you compare them, we can see that, for instance, version 5 only used DES for encryption. We know that DES is not very good. Version 5 says you can use whatever encryption algorithm you want. Version 4 only used IP, which is not a big problem because most using IP, but in version 5 you can use other types of network protocols. Version 5 uses this abstract syntax notation .1. We'll talk about it later if you don't know what it is. The ticket lifetime in version 4 was only 21 hours, which was a problem for some servers that you would like to be able to set up very long ticket lifetime. Say a log server where you only send log information. You might want to have a ticket that lasts for months in such situation. It's not critical to change keys that often or tickets. Authentication forward and inter-realm authentication was added, so we can actually have several realms. Version 4 only handles one realm then. And then there are some details about how things were encrypted and how do we handle keys and so on, which also changed. So version 5 is a better version, but still version 4 is actually used. It's an old standard now, but it's still used in some places. So in practice, well, we have these two versions, but if you have a choice, you should of course go with version 5. Version 5 is the latest version now. It's quite old. What they've done instead of making a new version is that they have added extensions, so you can do extensions to the current version. So if you find some new algorithms or a new type of exchange, a new type of network protocol, for instance, you can add that into as an extension instead of changing the actual version of Kerberos. So everything works the same with just technical details that are changed then. To use Kerberos in network, you need to have a key distribution center. You need to have a Kerberos system first. And if you don't want to manually distribute these keys, you need to add some other way to distribute the keys. You can manage with manual distribution, but it doesn't work if you have hundreds or thousands of users. So then you need some other automated way to distribute keys. You also need to have what's called Kerberized applications, because when a user at the client starts an application, it's that application that actually starts the communication. So for instance, your mail client on your system needs to know about Kerberos in order to use this. It needs to know that when you authenticate, it should go to the Kerberos server to get a ticket, and then it should use that to actually reach the mail server. So unless your application is actually built for Kerberos, it wouldn't work. So in a typical situation, you might have some application that doesn't work in this situation. But today, I mean, Kerberos have been around for so long that there are quite a lot of applications that are ready to handle Kerberos. Okay, so let's take a break here for about 9. Yes, a question.
What are the alternatives for Kerberos? Any alternative if you're not using it?
Alternatives Kerberos, well, there are no other standard protocols really to handle this situation. We will come back to later on. You can handle, I mean, the important thing is that you talk about users and credentials of users need to be stored centrally somewhere and be able to check them. There are other ways to store that information. We have, for instance, LDAP, and we have Radius. These are other ways to handle, store central information and check authentication. But there is none that tries to handle this as a complete solution as Kerberos is doing. Right, okay, break.
Like assignments. The network wants assignments as well. The networks want assignments. They still have markers. The sapphire tastes like chemicals. It tastes like window cleaner.
Where do you get it from?
From Willis.
It's too healthy.
Too healthy? Ah, but cheap.
Make the joke, okay?
Maybe, I don't know, 3. not the cheapest Apple, but it's the one I like the most. And it's still pretty cheap to an Apple.
Well, I think the press room maybe 10.
For an Apple?
Well, together with the copy list.
Right, I don't want to see. My Slack completely stopped working yesterday on my desktop.
You what?
My Slack. Like completely. I have no clue. But I'm gonna contact them because it's ridiculous that I can't fix it.
You have the desktop application. And it's not working.
Here it's working, but on my house, nothing. Zero. I'm trying uninstalling it, reinstalling it, deleting the configuration, using another desktop environment. Nothing. That's the problem. It doesn't say anything, so I can't
I had
Google
the
it.
same problem during the summer.
Really?
I had the summer times, I didn't know why. But I mean, I think it was also adopting something on the computer continuously. So maybe more updates that are required for that updates on this computer. I think we had some issues here also.
Was your problem?
Updates.
Was your problem that it opened in the taskbar, but you didn't have a window?
I had a white window.
Oh, no, I don't even get a window.
Well, I don't exactly remember, but I know it has something to do with.
I'm gonna see.
sure it has something to do with updates.
Yeah.
So, I mean, did you update it?
Yeah. Yeah.
Did you read about updates that they cause issues? Because I couldn't use my VPN either.
Really?
And I read about that Windows update causes issues with several applications. So they are all. It was during summer.
Right.
So.
No, in my case it was Firefox that updated, and a couple more Plasma desktop. It wasn't really.
Well, if it's a desktop, can you open it in the browser?
Yeah, my browser was fine.
So it's a desktop application. It's
Right.
obviously something with the.
Yeah, but the thing is, I tried another desktop environment, so something that wasn't related at all to the one I was using, and still nothing. It would open on the taskbar, but it wouldn't actually open. I'm actually gonna talk to the.
I'm sure it's something like that.
Could be.
Compromised updates.
Yeah, it could be. I'm not sure. Maybe they know about the problem.
Yeah. How long have you?
Actually, the first version was really good.
Oh, good.
Read it through, but the second is very like
Many tools I don't understand, like C++.
I don't participate.
This is open SSLs.
so you find
I tried to download, but there is nothing.
Information communication. Information communication technology is just IT is like IT.
I don't know how that works. I tried to access the CSS
I log into
but he said
Okay, let's start again with X509. So this standard also is about authenticating, but the scope is entirely different. Here the idea is that we have a distributed set of servers that maintain this information about users. In Kerberos we have one central place. Now we say let's have a distributed system. We can have many different servers who keep different parts of that information. And the information that they keep are then in the form of certificates. And these certificates then contain, as you see, a public key of a user, and it's designed with a private key of the owner of that database, a certificate authority. So also you see that now we're talking about public key encryption and not conventional encryption. This protocol is used in a lot of different places on the internet. There are endless of protocols who actually uses these certificates in order to get authentication. For the encryption here, we said that using public and private keys. And RSA has been the recommended encryption algorithm to use, although that has changed now, so you can use ECC as well. So this is what we store on this distributed server. We store certificates and also a certificate revocation list. So these are two different data structures that we store. The certificates as itself are also distributed, so they are can be handled individually. But here we have the information that a certificate contains. And as you see, we have different versions of this protocol X509, and each version have added more information to the certificate. So we start at the top with a version, which is then 1, 2, or 3. Then we have a serial number for the certificate. And that serial number is not unique, because we have many different certificate authorities. So the serial number is only unique within a certain certificate authority. Then we have signature algorithm identifiers, which contains information about what type of public encryption algorithm is used here, what algorithm it is, and what parameters. And the parameters could be, for instance, key length. It could be initialization vector, or whatever, parameters that are needed for that algorithm. And that is for the signature. And the signature is done by the CA. So it's information about the certificate authority's key that is used to sign the certificate. Then we have an issuer name, and the issuer name is the name of certificate authority. It's just a plain name, a text field. Then we have a period of validity. Not before, not after. So we can pinpoint exactly at this time it will start to work, at this time it will not be valid anymore. Anyone who knows what the time of validity typically are for certificates?
4 years?
4 years? Could be. No, it's typically less. Yeah.
HTTP is what, 1 year?
1 year is quite common, that validity. In some critical situations it can be shorter, and in some situations it can be longer, but 1 year is quite common actually. And the certificate authorities are commercial companies, which means that if you get a certificate, you have to pay for it, typically. and then after a year you have to pay again to get a new one. If you pay a little bit more, you can get one that lasts for several years, but that's not recommended, because that means it's also more vulnerable for different types of attacks for a longer time. Okay, then we have a subject name. The subject name is you, if you get a personal certificate, or it can be the name of an organization, or it can be the name of a specific machine, server. Then we have information about the subject's public key information. So similar to this one, but now it's the key that this certificate is about, and information about that. What algorithm, what parameters, and the key. What key is this?
Public key?
Yes, this is the public key, not the private key, because the private key we should keep secret. And this is a document that we can distribute on internet, so we don't want the private key information here. But the public key is fine. As see, that is what we have in version 1. And also at the end here, in all versions, we have the actual signature, who's verifying that this information is correct. And what do we do here? Well, again, we have information about algorithms parameters, which is actually the same thing as we have here. So it's added again, just for convenience, actually. And then we have important thing, the encrypted hash. And that encrypted hash is then covering all the information here, hashed and then signed with the CA's private key. And that is the encrypted hash that we add here. In version 2 and 3 we have then added things. In version 2 we added information about issue unique identifier, subject unique identifier. Because the issue name and the subject name here were not unique. That means that if you created a version 1 certificate, you can say that I am VeriSign up here. And nobody would know what VeriSign it is. But down here you have a unique identifier, so each certificate authority has a unique number. So there is an authority that controls that they are unique. And within that you have a subject unique identifier, but again it's only within that certificate authority. So it's just to clarify, make it precise who have signed it and who is it for. And then in version 3 we added something called extensions, which we'll look a little bit on later on. So it's version 3 that is used today. This certification revocation list we'll also come back to shortly. Remember this from last week? This is how we create the signature. We said that this is the certificate. So here we have issue name, we have a subject name, we have a public key, and then we take the hash, and then that hash is encrypted with the certificate authority's private key. So it's a encrypted hash, and then we store that into a certificate in this last field here. So this is now the entire certificate, which can be distributed on the internet, for instance. Who can check a certificate? Well, we can have this picture. Who can check that this hash is actually consistent with the information in the certificate?
Anyone?
Yeah.
Anyone, because you need the public key of the CA, and this is published.
Yeah. What you need is the public key of a CA. That's the only thing that is needed in order to check the certificate. And as all public keys, that should be common knowledge. It should be published. And actually, if you look at public keys for certificates, they are published in many different places because it's important that that is correct information. So they publish it on the home page, they publish it through different key servers. You can actually call them up and ask them for the fingerprint of theirs so we can check that it's a correct one. So that is easily available. So anyone can do that. And what can we do with that information? If we now have the public key of a CA, what does that tell us about this information?
That this information actually came from the CA because they locked it with their private key.
Yeah. It says that you say that the information come from the CA. Actually, the certificate is typically could be created by anyone. What the CA have done is signed it. Well, often they are also involved in creating it, but that not necessarily. But we know that they have signed it at least. That means that the CA somehow vouches for that information in the certificate. They say this is correct information. And the main part of that correct information is that we link this public key to this subject. This could be, as I said, a server or a person, but now the CA says, yes, this subject is linked with this key. So to check this, well, normal for digital signature, we take a cryptographic hash or a secure hash of a message. We sign it with our private key, and on the other side, we can check it with Bob's public key. Bob now being the CA then, and Alice, someone on the internet who would check this. And as long as the decrypted version of the signature matches the hash of that information that we calculate ourselves, if they match, then the information is correct. If someone tries to change the certificate or the content of it, change the subject name, for instance, I mean, the signature would still be the same. But if we take the hash now of that information ourselves, it wouldn't match any longer. So that's how we can know that the information is correct in the certificate. So we have certificate authorities, and they offer this as a service then to issue certificates. Typically, you have to set up some type of negotiation, some type of agreement with a certificate authority to be able to get certificates. And in that process, they check who you are. We'll come back later on that they have typically different levels of how hard they check that. But they do some check at least to make sure who you are. A user who have access to the public key of certain, say, can recover the user's public key that was certified. And no other part than the CA can modify, as said, because if you modify it, the signature won't check up anymore. Now, we said that there are many different certificate authorities. So I have a relation with one, and then I start to communicate with someone that uses another CA. And there are hundreds of them. I don't know them all. So how can I have trust in that certificate when a packet arrives that has been signed with someone who I have no idea about? Well, I trust my CA because I have a relationship, but not the other. And to handle this situation, we have a certificate authority hierarchy. They have a relationship between different certificate authorities, so they cross-sign their keys. Which means that, well, in reality, if I have a CA here and another one has a CA here, we don't know about each other, but then there is a link of signed certificates that you can follow. So when you check it, you check that there is this link here going from the CA you don't know about to your CA. And if that link exists, they have signed each other. That means that they are vouching for each other. And now we can start trusting certificates over here as well. Of course, this requires us to trust the entire link and to trust that our CA is actually responsible enough to not cross-sign certificates from others if they are not legit. Yeah, I think that's enough. Sometimes we have to revoke certificates. Revoke means that we say that, okay, there is a certificate here, but I don't want it to be valid anymore. Why would we want to do that? Well, mainly if the private key has been compromised. If we know I have lost it, someone else knows about it. Of course, I would like to revoke certificate so that person who has now access to the key couldn't misuse that information. Another situation could be if we no longer use this. We said that this is typically a business agreement. If I change CA to another one, we would like to revoke all of our old ones and create new one with our new CA. Or the worst case, the certificate of authority certificate is compromised. Because if that happens, the one who has compromised that could start issue false certificates that look correct. And we would need to be able to revoke all of those. To handle this revocation, each certificate maintains a list of revoked certificates in a certificate revocation list. And that was the other data structure that we had here to the right here. So this is this list here. And as you see, it starts by saying that these are parameters for the algorithm that this CA is using. And this is who we are. This is when it was updated, and this is the next time when we plan to update it. It can be updated earlier if needed, but there is a plan, which means that if we had checked this one, we know that we should go and check at this time again, because then it should have been updated. And then it's just a long list of revoked certificates, which are, as you see, the certificate serial number, one up here, and the revocation date, when it was revoked, which means that the not after date is not valid anymore. And then comes the next one, the next one, the next one, and then at the end, the entire list is signed. So if you get a certificate on your hand and want to check that it's valid, yeah.
Does this not have a issuer unique identifier? Or is the issuer name unique?
Yeah, I think actually they have changed it. So the issue name is not only a name, but it's also stored with that certificate of authority, so we know who it is anyway. So, but yeah. Now you get a certificate in your hand. What do you need to do to check that it's okay? Well, the first thing you have to check is that the signature is okay, but that is matching. The second thing you need to check is that the period of validity is still okay. And the third thing you have to do is go to that certificate authority and check that it hasn't been revoked before. Now, say you go to website XYZ, some type of web shop, and they have a certificate to secure the communication between users and that web store. So up pops, well, how do you see first that it's secured by a certificate when you go to a web store?
In the web browser? Or
Yeah, in a web browser.
usually in the top left.
Yeah.
There'll be a lock or a
There's
key.
a lot.
You can see a visual sign in most web browsers say that, as I said, a lock There can also be different colors depending on the status of a certificate. Can be green color, then all the checks go. There could be a yellow color saying something is not quite okay with the certificate and so on. So you can get different warnings here. But the lock only says that there is a certificate and it's used to encrypt the information. It doesn't say anything about who that person is who is behind that web store. Yeah?
Some browsers, like for example Firefox, are just blocking websites which they don't trust.
Yeah, we'll talk a little bit about extensions to get this more secure. But yes, sometimes websites can be blocked if they don't contain good certificates in some way, whatever good means then.
I have a question.
Yeah.
Somebody asked.
Another question. Can you define certificate? Well, the definition of a certificate is just this information here. This is a certificate. That is what the certificate is. Information about a public key and a person and how to use that public key. The algorithms that is used for it. That's the only thing that a certificate is, really. And then it's depend on how you use it in different situations. That can be different. So if you come to a place, you see a keypad, that doesn't mean that everything is okay. Can be a certificate that has but no one has checked. It can be a self-signed certificate by the web store itself, no CA at all. And in many situations, when you get to these places, you get a warning saying that this is something problematic with your certificate. And then you can go and check the details of it, or you can say, I trust it anyway. And what do you think people do? Yeah, trust it anyway. Exactly. So unfortunately, that is a limitation with certificates, that people trust them in situations when they shouldn't trust them. The actual authentication procedure when you have a certificate can be different. There are different modes for it. Yeah, question.
If I would like to attack the circle, like if I would like to get hold of these certificates, so if you have this web of trust with the CAs, I would just need to get hold of one of them, right? Like if I was a government agency and I would like to compromise your authentication, so I would just need to get hold of one, right?
Okay, so the question is about this web of with trust chain here. If you would attack this, say that you can control this CA, then you can control one. Yeah, if that CA is already in this trust chain here, if you start issuing certificates here, then they would be trusted by anyone else as well. But hopefully all the other CAs have eyes on each other, so they would start seeing that something's going on, and then they would exclude that CA from a list.
But that's like hopefully.
Yeah, that's hopefully so. There is no mechanism here that automatically can handle that. Also, we talked about this situation here, that a certificate authority certificate is compromised. That has actually happened. So for quite many years now, maybe 10 years ago, something like that, a hacker from, I think it was Iran, but I'm not sure, could be some other, actually managed to hack and compromise one of the major certificate authorities' private key, and started to issue certificates for Microsoft services that pointed, of course, to rogue servers. So when people went to Microsoft, they came to rogue server. The certificates showed up okay, potentially that could have created a lot of problems. But it was, they found about it within a day, and they didn't really have time to be able to exploit this possibility. But what happened is that they had to revoke all the certificates from that CA and start from the beginning and create thousands of new certificates, or tens of thousands of new certificates. And of course, the trust for that certificate authority was not great at that time. And there have been a few other incidents as well with things where there could be potential attacks that have worked and so on, but it's not so obvious that it has been worked. But this entire trust chain is a little bit fragile, and it is built on trust between a lot of different parties. So we should know that when we're using services that are user certificate, that there is a small risk that it's not actually correct. Like always in security, we are never fully secure. Okay, very brief about this one. It just shows that you can use certificates in different scenarios when you authenticate. So here we have just one party authenticates the other. And this is the typical situation when you are going to a web store, for instance. The web store has a certificate, it provides that, which means that you could have some trust in that web store, and it can be used to set up an encrypted channel between you and that web store. And then information can be encrypted in both ways, but it's only the web store that authenticates towards you. You don't give your certificate to web store, typically. You can have both ways. Both need to authenticate to each other using certificates. That is something that is being more and more common. For instance, if you use bank ID in Sweden, something like that, then you actually have a certificate behind you that also authenticates you to the bank or to some other service. And then there is this called three-way authentication that just adds an extra step to make sure that both parties have been authenticated and both are aware that both have been authenticated. So it's not hugely different. Version 3, as I said, the last version of well, after version 2, there came up a number of different ideas on how to extend the protocol or the standard. And they realized that we couldn't make a new version every time. It will be too hard to handle. So instead, they made the version 3 to be flexible, so you can add different things depending on your needs. So we have extensions. So a certificate can hold one or several extensions. And each extension has then an identifier to tell us what type of extension it is. Criticality indicator, which tells us is this a very important extension, or is it not that important? And then if you get a certificate and it says that this extension is very important, you need to comply to it. And if you don't understand that extension, because it's an extension that you don't know about, then you just have to discard that certificate. You couldn't use it at all. If it's just information, not critical, you can still use a certificate even if you don't know what that extension is about. And then we have a value, actual content. Some examples of these extensions. There is one called key and policy information. Say convey information about the subject and issue keys, and policy about how to use them. In what situation can we use these keys? Are there specific extra steps what they need to perform in order to ensure them and so on? So we can give a policy for how to handle these keys and the certificates. Another one is called certificate subject and issuer attributes, alternative names, alternative formats to identify subject and or issuer. And a third one, certificate path constraints. And this is a little bit reaction to what you brought up before, that we have lots of CAs and who can we trust? And here you can say that, well, we would only trust a few here. We will limit who we'll actually trust. There are others as well, and it's a no-ending list, so we can add more extensions. And actually, you can create your own extensions if you want to, that only your organization know what it is about. That's fine. So now we have certificates. And we talked about this chain of trust between certificate authorities. But really, to make this work fully, we would need something called a public key infrastructure. We need to have routines to handle how to create, how to check, how to revoke, and so on, all the certificates for the entire internet. So a public key infrastructure consists of all the things that is needed to handle this. Computers, different software, people, policies, and so on. And there is a standard called PKIX, which is, as you see, really the Internet Engineering Task Force Public Key Infrastructure X509 Working Group. Nice short name. They are one responsible for the public key infrastructure, how to handle it. I see it's part of the Internet Engineering Task Force, so it's part of the Internet Board then, and who handles IP addresses and domain names and all the standards on. So it's the control body, which is actually quite a nice control body because it's not controlled by any specific country. It's really an independent organization where people from all the world can be part. And then it's sponsored by different countries, so they are not fully independent, but more or less. As you see, there are different parts here than is in what they define as a public key infrastructure. We have end users here who should be able to register in installation, create key pairs and so on with the help of a certificate authority. But it should be instigated by a user here. Users can themselves revoke a certificate. The only thing you need to revoke a certificate is that you know a private key. So anyone can revoke a certificate. But that's not a problem, because if someone has found out your private key, you would actually be quite happy if that person revoked your certificate. So that's not a problem. In the CI part here, we have, as you see, different types of actors. We have certificate authorities themselves. We have something called a registration authority, who helps to manage this revocation list. The certificate authorities can use special revocation issuers. And we have this cross-certification between certificate authorities. So all of these require certain type of policies, how to set things up, who decides what type of information do we need to send, to whom, what is the format of that information, and so on. So all of that is governed by this public key infrastructure. A little bit on lifetime public key. We always said that keys should have a limited lifetime. And of course, when you talk about certificates, the key and the certificate lifetime is the same. Because if you issue a certificate with a certain time when the certificate is no longer valid, then you should create a new key to get a new certificate. In theory, it is possible to reuse your old key and just get a new certificate for it. But it's probably not a good idea, because the longer you use a key, the bigger the risk is that it will be compromised. So lifetime is just you generate the key pair, you get certificate, and then for a long time it's used to validate, and then it expires, and then you have to update, get a new key. And throughout this, you have this public key infrastructure that is controlling all of this. Now, as an extension here to certificates, Google proposed a standard, as they called certificate transparency. Especially to handle some flaws in SSL, which we'll talk about later on, but in general to handle certificates. And the idea was here to be able to see if a certificate has been, as you see, mistakenly issued or maliciously acquired from some certificate authority. So the structure is like this. Down here we have a client, that is us. We extend our computer with what's called an auditor here. And that auditor is in contact with a log server that is monitored by certificate authorities that are part of this scheme here. And then we have some website here that has a certificate that is issued by this certificate authority. So this is the normal way we issue it, and then the normal way is that we use it down here. But the idea with this certificate transparency is that we should have a channel around the user here, because normally we contact the website here and get certificate, and then we use it. We might use the key from the certificate authority to check it, but we don't really go to the certificate authority when we do that. We only use the key that we have stored and saved. So, but now we have a live communication. So whenever we go to a certain site, we actively check in this log server. And this certificate authority monitors the use of its certificate and can immediately, when see something suspicious, notify the log server, who would then tell the auditor to block the use here of a certificate, even if it hasn't been able to revoke it yet. And we can issue different levels of warnings here. So the idea is to be able to quickly find out about use that is not correct. And to do that, it uses the information from different clients. So we log things here, and the monitor checks how that certificate is used, and based on that information we can find that the certificate is incorrectly used somehow, and then we can block it. Otherwise, if we don't have that, once a certificate authority have issued a certificate, it has very little control over that certificate, how it's used. But this makes it a possibility to have some control over it. So that was Kerberos and X509. Now we'll talk about some other concepts together with authentication. So federated identity management is quite a big thing, as it deals with identification across multiple enterprises and numerous applications supporting large number of users. So the idea with federated management is to be able to scale up authentication, not only within an organization, but not the same idea as certificates, because certificates is only really sharing keys. This is identities and how we can use identities. So see, there are a number of elements here. We should be able to authenticate people, authorize them, what are they allowed to do, accounting, so we can keep track of what they're doing, potentially billing as well, if that is involved. Provisioning means that we should be able to roll out. We create a new server, we should be able to roll out it to new users. We should be able to include new users in the system and so on. Need to be some automation here because we are talking about situations with hundreds or millions of users. Delegated administration. The idea is that we have many different organizations involved here. And that means in order for this to work, we actually have to delegate some administration to someone else. We couldn't do all the things ourselves. That also means that we have to trust someone else. Exactly what we delegate here can vary. Password synchronization. That is an important aspect, and that is one of the driving forces for federated identity management. You are using a number of different services. You would like to have the same user password on all of them. You don't want to remember 100 different users of passwords. And as an extension of that, also single sign-on. When you have signed in once per day, you don't want to give your credentials over and over again. Self-service password is set, and then actually federation, the rules around it. If you think about how you use internet today, do you use this? Yeah? Can you give examples of when you use it?
For the university.
For the university?
Log into my Moodle or to your Gmail account.
Yeah.
The same sign
Yeah.
date.
Within the university, we have many services. You have password synchronization, single sign-on. That could have been made as a federation, but it doesn't have to be. It could equally well be a Kerberos system. But if you think about eduroam, that is a federation. You're using the same credentials if you go to university in some other country, eduroam. So that is handled by a federation. Yeah.
You're using Facebook to log into apps or websites, or Twitter or Google.
Exactly. These big IT companies, Facebook, Google and so on, they are now taking a role here and providing authentication as a service in exactly this type of federated identity management system. So what we have are what we call principal. These are people. So you are a principal. Principals authenticate against an identity provider. So this could be Google, for instance. Principals provide attributes. These are attributes about ourselves. Attributes we could provide is our phone number, our address, our age, whatever. There are different attributes that we have to give when we sign up. Attributes can also come from administrators. Those are attributes that we couldn't assign ourselves. When you are at the university here, for instance, you get an attribute as student with your user. I have an attribute as teacher. So when we get to a system, we get different rights depending on the attribute we have. Those we couldn't control ourselves, so we couldn't change our role here. And then we have a data consumer down here. That is the one who's using this identity provider. So whenever an attribute tries to log in here, the data consumer contacts the internet identity provider, who manage, as you see, different types of information about us, and it also extracts attribute that is important for it to decide on if that user should be able to log in and what rights that you should have once you have logged in. So here we have identity provider. Typically this is the process. The user log in to the identity provider. We get different attributes here from an administrator to control what we can do. The identity provider contacts the service provider, who then issues the actual logins. So we go to a site, but we identify, authenticate ourselves against the identity provider. So all of those are involved here in that process. In the book, we have these examples of different types of federation we can build here. Here we see an example first of where users actually are linked. So we have users in different systems that they are linked together. So we know that the user called Joe here is the same user as down here. So that's quite low level of federation. Here we have more as how it typically should work, where we have federation based on roles. So in one system we have users and roles together with that. When we go to the next system, we are not known as users here, but we come with our role, and then we can access depend on that. And then we have something called chaining as well. We go to one and then they can chain it to the next one. So there are different ways to build it. A little bit on the standards used here to build federations. There are quite a few. XML, as you know, is standard to manage information in a structured way. And that is used to build the data structures that we need to send. SOAP, Simple Object Access Protocol, is quite an old protocol in order to make distributed computing. You can send a request from one computer to another to make some type of computation on that other system. So it's a way to send and access to another system. Web service security are SOAP extensions, you see, to handle different web services. That is the basis for federations. And you have this security assertion markup language, which is, as you see, XML based, but contains information about users, the rights of users, what information we need to send. So in principle, we have different ways to communicate, and we have different ways to structure our information. And then we have something called Shibboleth, which is originally what's called an Internet 2 project. That was a big project in the United States, maybe 20 years ago, something like that. What's called Internet 2, where they said that, okay, let's start from the beginning and see what should we have done when we built the internet if we started now instead of 50 years ago. And they developed quite a lot of different things. Some of the things never were used, but some of the things have been merged into what we call internet today. So it's not an entire new internet, but just there was free hands of trying to build something new. So that is a protocol just to handle this inter-domain trust that is needed to build a federation. And actually, if you are looking at Eduroam is built using Shibboleth as a way to communicate between systems, which makes it possible for you to first contact locally the system, and then it will forward that request back here to LNU to check your credentials. And the information is structured using not SAML, but SAML 2, which is the newer version of SAML 1. So these protocols are, or standards are used to build federations today. I think we skip the trust models, and we don't have time for Kahoot today either. I have a couple of Kahoots waiting, but sometime we will have time for them. So don't forget you have teaching session or tutoring sessions today, and we have a new lecture on Thursday morning. Okay, thank you.